Okay, 8.3 applications using accumulation functions and defined integrals. Okay, in the last section, we were doing applications involving displacement, velocity, acceleration. Now we're going to look at other scenarios where we could also use integrals to evaluate a situation. So up here it says the integral of a rate of change. The integral of a rate of change, if you integrate a rate, you get the net change. Okay, if I were to integrate meters per second, I would end up with a result of meters, and it would tell me the change in the meters during whatever time period it is. Okay, let's think about that as we do these examples. So example 1, a storm has washed away sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was decreasing during this storm is modeled by R of t equals e to the negative sine t feet per hour, t hours after the storm began. The edge of the water was 200 feet from the road when the storm began. If the storm lasted 4 hours, how far is the water from the road after the storm? Okay, so let's see. So the water and the road. I know that we start off with 200 feet. The water starts at 200 feet from the road. So let me start off with that idea. We're at 200. During the storm, the water gets closer to the road. So we're expecting a smaller answer. The rate at which the distance between the road and the edge of the water was decreasing during the storm is modeled by R of t. So this is R of t is a rate. I know it's a rate because they told me it was the rate at which the distance between the road and the edge of the water was decreasing. I also know it's a rate because it's measuring feet per hour. Okay, so that's telling me the change in the road as the storm progresses. Okay, now as the storm progresses, the edge of the water is getting closer to the road. So I'm going to subtract the integral of R of t dt. Now, how long do I want to measure the change in the road? Over which period of time? Well, the storm lasted 4 hours. From when the storm started for 4 hours, I want to see the net change in the distance between the road and the edge of the water. So then I do 200 minus this, and I will get the distance from the water at the end. Okay, now I'm going to put this in my calculator. Okay, and it is okay for me to just say R of t dt here because R of t is clearly defined right here. So we know what we're talking about. However, when I put it in the calculator, I'm going to do 200 minus the integral from 0 to 4 of e to the negative sine x dx. And I'll put the entire thing in my calculator, but my setup can look like this. Okay, when I put it in my calculator, I get 196 point, let's keep 4 decimals, 196.9373, which is less than 200. So the water and the road did get closer. Now, what is the units on this? Well, we started at feet. These are feet. This was a rate of feet per hour, but I integrated it and it turned into feet. So this is going to be feet. Okay, let's go ahead and look at another example. Example 2. A store is having a 5-hour sale. The rate at which the shoppers enter the store after the sale begins is modeled by the function e of t. So e of t is a rate because they told me it's the rate at which the shoppers are entering. It's measured in shoppers per hour. When the sale starts, there are already 70 shoppers in the store. Right, but do not solve an equation involving an integral to find the time x when the number of shoppers in the store is 200. Assume no one leaves the store during this time. Okay, so let me think about this. What do we start with? Well, when the sale starts, there are 70 shoppers in the store. So I started with 70 shoppers. Okay, and then the shoppers are entering the store. How many shoppers are entering the store? They don't tell me how many, but they tell me the rate at which the shoppers are entering is e of t. So if that's the rate the shoppers are entering, the number of shoppers entering should be the integral of e of t dt. Okay, now what should my variables be? Let's look. We want to find the time X when the number of shoppers in the store is 200. So I want to add it up until I get to 200 shoppers. Now, what should my time be? Well, I need to go to X. I start when the sale starts. So the sale starts at 0. There's some time X at which we reach 200 shoppers in the store. So this is 70 plus however long it takes to get to 200 shoppers. And I don't need to solve it, I just need to set it up. So I'm going to leave it like this. Okay, let's go ahead and look at example 3. Okay, example 3. Water is pumped into a tank at a rate modeled by R of t liters per hour, where R is differentiable and decreasing from 0 is less than or equal to t is less than or equal to 8. Selected values of R of t are shown in the table. At time t equals 0, there are already 5,000 liters of water in the tank. Okay, let's consider, we start with 5,000. So there's already 5,000 liters of water in the tank at time 0. Okay, now why is this 3,000 if this is 5,000? Well, this 3,000 is just the rate at which new water is being added to the 5,000 at that moment in time at t equals 0. Okay, and then this is the rate. This is the rate. It looks like the rate's decreasing. Or actually, they told us it was decreasing. Okay, so the question, first question is, what does 0 to 8 r of t, the integral from 0 to 8 of r of t dt represent? Okay, well, r of t is a rate. It's the rate in liters per hour. So if I do the integrate, if I integrate a rate, I should get the net change. Okay, what is it a change in? The change in water in the tank. The amount of water pumped into the tank in the first 8 hours. Okay, if I do the integral, I get the amount of water pumped into the tank in the first 8 hours, or the amount of water added into the tank. There were already 5,000, and then in those 8 hours, this is the amount of water that gets added to that 5,000. Okay, B, estimate the integral from 0 to r of t dt using a left Riemann sum. It's been a while, but we know how to do those still. Okay, let's see. Let's go with 1, 2, 3, 4 of them because it's set up for that. Okay, remember Riemann sum, the width is 1. Since it's on the left, I'm going to take the height on the left. So 1 times 3,000 plus from 1 to 3, the width is 2. The left height is 2,500. Okay, and then from 3 to 6, the width is 3. The left height is 2,100. Then from 6 to 8, the width is 2. Height is 1,500. Okay, that's going to give me an approximation for the integral from 0 to 8 of r of t. So that's about 17,300 liters of water added in that first 8 hours. Okay, last question says, based on this estimate, how many liters of water are in the tank after 8 hours? Okay, well, we added 17,300, but we did start with 5,000. So this is 5,000 that we started with, plus the net change in those 8 hours is positive 17,300. So we ended up with 22,300 liters of water approximately in the tank after 8 hours. Okay, one last example. Example 4 is the same scenario, but this time the table of values represents W of t, the number of liters of water in the tank at a given time, measured in hours. So this is reflecting the fact that at time equals 0, there are 5,000 liters in the tank. Time 1, now there's 9,800. Okay, so part A, what does the integral from 0 to 8 of W prime of t dt represent? Okay, notice they're saying W prime of t, which is the derivative of W of t, which is the rate of change of the liters. So they're asking me to integrate the rate still. Since they're still asking me to integrate the rate, I'm still going to get the net change in water over that time period. Okay, so for the interpretation, it's still the amount of water pumped into the tank during the first 8 hours because I'm integrating the rate, which is still going to give me the liters. Okay, part B, find the integral from 0 to 8 of w prime of t dt, which is the same thing we did, but we approximated doing a Riemann sum. But our table is not representing the w prime information. They're giving me w of t. Okay, well, if I do the integral of w prime of t, I get w of t, because the derivative of w of t is w prime of t. So if I do the integral, I get w of t, and they want me to evaluate this from 0 to 8, which means I'm just doing w of 8 minus w of 0. W of 8 is given on the table because this table is w of t, so that's going to be 22,000 minus w of 0, which is 5,000, so that's going to be approximately 17,000 liters of water that was pumped into the tank during those 8 hours, which makes sense because there was 22,000 at the end, 5,000 at the beginning. That's the net change. That's the definition of net change.